There's nobody there. All right, so we got that. And let's see. We got 4 minutes, something. Oh yeah, I was wondering why it's taking so long. Yeah, the PDF is like 10 meg. And the PowerPoint is no, I'm firing up the other one, but basically I clicked it three times because I thought it's not downloading it, but it did download it 3 times. Yeah. And this is a pretty fast connection usually.
Make sure it works. Just go down. It's like a movie. Like go down like a few slides. Right, next one. Another one. Just go and click on that. Yeah, it should work.
Is that okay? Yeah. Yeah, then it's set up with the Zoom thing. That's a nice photo, huh?
That's very.
Yeah, down the hall to the left.
Yeah, all right.
Elevator.
Yeah, it's time to leave. Break this night here or something. All right, so let's see if this thing's working. Is there a Starbucks still like near TUC or something, or
You see,
it's inside TUC?
it's down like some library has one.
Oh,
Yeah.
oh yeah, I
And so
forgot
it's-
that because I went to take him to Starbucks, but that place isn't Starbucks anymore. One over by the rec center.
Oh,
So they moved it to Langsam, huh?
yeah. And they also have.
Yeah, I remember that now. Now that you mention it,
Yeah.
yeah. There's 2 Starbucks that are within, we just had to go the other way. I just forgot it. Yeah. Anyway, so you can use this, you can draw things there if you want, you know. And then, so the idea is like maybe, like you can present your slides, but they'll interrupt you. And then just make it kind of into a discussion. And they can even ask things about your nanocomposite stuff. And so he did, all right, so it's interesting because we're doing stuff with supercritical solvation of polyolefins using butane. And then I looked you up like on Chat GPT, which turns out to be a great thing to get a bio of somebody. And it said like, oh, he did his PhD with Johnston at MIT, and I knew that wasn't true. So then it said like somewhere else, and I said, what about Suter? And it said, yeah, Suter and Reed. And anyway, it went through that, but then it's all about supercritical solvation of polystyrene, which is like kind of a coincidence because Procter and Gamble's got this thing called Pure Cycle, where they're using alkanes to solubilize polyolefins for reprocessing. Yeah, so it's like your PhD thesis, what, 1989 or something, and like whatever, how many years later, right?
Well, this thing, the supercritical fluid, it keeps coming back.
Right, because I did some when I was at Sandia, and then anyway, I worked with a guy, Ehrlich, who's at Buffalo, and then he was at UMass, and then we did some stuff together. So I had a little bit of my foot in the supercritical water, you know?
But he
and then-
was doing ethylene, right?
Right, no, well, he was doing propylene and ethylene and ethane and propane. I don't think he ever did butane
I don't think, I've never seen butane.
and
but I
polyolefins. Well, butane's nice because it comes in a can, not in a tank, right? So basically, it's something like 2 or 3 atmospheres.
I worked with ethane, I think.
Yeah,
supercritical ethane.
that's gonna be nasty. But to get supercritical, you need 50 megapascal and 150 to dissolve stuff in it, though. So you still have to crank it up even with butane.
So we had this compressor that was like that.
Yeah, that's the issue, the compressors, but anyway, so.
Ethane is not fun.
Yeah, so anyway, his PhD was on that stuff, and it was with polymers. Then he went to IBM Almaty, worked with Tom Russell and Do Yoon, who are like 2 guys that were doing surface coating of polymers, you know, for films. And then at that time, so Russell and Do Yoon were Stein guys. Somehow he became kind of a Stein guy, I guess he must have. Did you become a Stein guy then, or? So it's kind of a funny thing. You worked with the Stein people, but
That's
you,
right.
okay,
I don't even know if Stein knows like. He knew me, but he didn't.
yeah, well, he's dead, so anyway, so yeah. But anyway, I worked with Stein, so for grad school, and then so did quite a bit of stuff on films, surfaces, films with polymer, and then got a job at Penn State teaching, and then worked with Colby, who we've done some papers by Colby, right, on the polyelectrolytes and things. But you didn't do polyelectrolytes with him. You did like phase behavior or something, or and then dumped Penn State, got a better offer from Rensselaer. This is like classic. And then, all right, so Suter and Reed both also hop schools, right? So all your and Johnston was at Austin, so all your mentors hop schools, right? So he ends up being like a school hopper. Every time doubling his salary, you know?
I don't think it doubles ever.
Almost doubles, you know? So he's rich, you know?
No, double of 0 is 0.
Okay, that's true. Anyway, so he ends up at RPI and works with Linda Schattler, who's a nanocomposite was her main thing, you know? But she was more experimentalist, and here's this guy who's like, I always thought of as like molecular dynamics or something, but it seems like you're really an experimentalist originally, right? So somehow does like a do-it-all person. Couples up with her and some other people, and then walks out of there to Columbia with a nanocomposite is like kind of already has a nanocomposite thing, and then develops that into like the king of nanocomposite, like Mr. Nanocomposite, and then basically everything in nanocomposite to say Sanat Kumar. Right? So it's interesting. Anyway, it's interesting. The story I think is important to it. And now it's like recycling polymers. So to me, it's a downgrade. But basically, you know, so if you want to ask him questions about anything in polymer physics, and he wins the Ford Prize in polymers. It's like the highest prize of anything in polymer field. Like it's kind of like your label, the smartest guy. So he's here. So he's going to talk about this recycling business and kind of micro and nanoplastic, right? So but this afternoon he's going to talk about machine learning AI stuff. So at 4 o'clock in the Clifton Court, so totally different subject. So you can see there's a diversity of things going on. So anyway, so I think it would be good if we just have a discussion, I think, in a lot of ways. Like he can present some pictures and then just ask him questions about nanocomposites, AI, ML, machine learning, molecular dynamics, surfaces, thin films, supercritical fluids. He's an expert at all of those and probably some others.
That means I know nothing about nothing. Okay.
Well, anyway,
So you're going to kind of hear what he has to say about.
You guys see this picture? Know where that is, by the way? No? Actually, can I turn the light
Yeah,
down? a little
right
bit?
over in the right corner, I'll switch.
That's a better picture.
Yeah.
So this is the campus I'm at, and hopefully it'll exist in the next few. Moment, it's very unclear where we're going, right? That's the Columbia campus. And if you look over here, that's where the Palestinian protests happened last year. This is an urban campus. This is Broadway, right? And you could walk off Broadway into the campus. Apparently, there's the central street on campus is 116 between Broadway and Amsterdam. And the city gave that street to us. It's the only street in town where you don't have traffic, right? So it's supposed to be open, supposed to be a city school. People are supposed to come in and out. All that's changed now. All the doors are closed. If I don't have my ID, I can't walk onto campus. I mean, it kind of sucks where we are right now. I came to this country 40 years ago because it was this incredible place of freedom where you could come in and say whatever the hell you felt like, right? Now, today, I'm sorry I came. That's where I am. On that positive note, let me get started. I still maintain the fact that you guys have rights to ask me.
Like in Turkey, I was really surprised that you go to the main university in Istanbul, it's just exactly what you say, like you need an ID to get in.
Yeah.
So a lot of the developing world, I don't know about India, but the developing world, they have these, like Ethiopia doesn't have that.
Right.
But basically South Africa doesn't either, but basically autocratic countries have that.
Well, I didn't want to quite say that. I mean, I think we used to be a developed country and now we're becoming a free country, maybe developing in the backward direction, but we certainly are no longer first world, right? That's pretty clear. So this really is a gorgeous campus. This is at night, straight south. The stuff I'm going to tell you about today represents a new direction for me. So you're going to hear the passion of somebody who got converted, right? But that also means I'm going to open it up to you guys. Ask me any question you feel like. So the first third will be lots of pictures. I'm just trying to get you guys scared, right? So I have to give you motivation for why I started working on this problem. A couple of years ago, my kid went to school at Yale. So she was what they call a human rights major. There's like 20 kids who get the human rights major out of Yale. So they invited me to come in and give a talk, and I went and gave a talk about plastics and stuff, and I was doing nanocomposite. So the kids started yelling at me, saying, "You guys effed up the environment for us, and we're gonna have to un-F it up," right? Literally in those words. And I'm like, oh my God, they're absolutely right. So I said, I better do something about it. And so I started thinking, it's towards the end of my life, let me do plastics at the end of life, as a pun on everything where I stand and where the field stands. That's one thing. The other one was just before COVID, I went to UMass to give a talk. And my colleague Kumar, I don't know if you guys have heard of him. He takes me out for dinner and he says, what are you gonna do next? You know, I worked on composites for 15 years. And I'm like, I'm supposed to do something next, you know? And then I realized he was right, that I better do something different. And so I started working on this problem. You can see the first stuff we're doing is press. So this is absolutely new stuff. All right. So here's, you guys all know polymers, right? So I don't have to talk about tacticity and this kind of stuff, right? All right, cool. So this is the conundrum, and I want you to start thinking about it, all right? How many of you have seen this picture before, or something like it? Okay, let me walk you through it.
I teach a class on polymer,
End of life.
circular economy of polymers, yeah.
Cool.
Some of
you guys all taken it?
you have taken it, yeah.
All right, but I'm going to give you a slightly different twist on it. So let me walk you through this picture, right? So it's 500 million metric tons per year, right? It's of plastics we make, about $1 trillion, which is about 1% GDP. Out of that, about 80% is cast off after single use, right? 20% is sequestered, but about 400 million metric tons goes thrown out as waste. Okay, and it's what that waste is doing that I want to talk about. This is probably what everybody talks about, the whole idea of recycling, right? And I'm stunned by those numbers, right? It says 14% are collected for recycling, 2% gets recycled, all right? So let me ask you guys the first question. Why is that number so low?
Why is only 2% getting recycled?
A mixture of polymers that you, this is over designed and you can't recycle it then, if it's a mix between like PET and
Why can't I recycle something that's over designed?
like a bag of chips.
Yeah.
It has too many layers on it and each layer is doing their own thing. and,
Right,
you
it
know,
just means it's expensive, right? I mean, it's doable, but it's just a pain in the neck, right? So the real point I wanted to make, which is sort of, I could have made it in one line, but I'm trying to get you guys involved. Is that it's way too expensive to recycle, and that's why people don't want to recycle. That's why you have that number, all right? But I'm gonna make a different case for recycling today, okay? Which is, look at that box up there, right? 15% gets combusted into CO2 and water, and I'm not gonna talk about CO2 as a pollutant, I'll leave that alone, right? But 72% gets thrown out into the environment. What I'm gonna try and argue to you is that this 70% that sits out in the environment makes these things called micro and nanoplastic, right? You know that if you take a bag of plastic and you leave it out in the sun for like a year and come back, this thing is gonna fragment and create pieces, right? You run a rubber tire, it makes pieces, we all know that. What I'm gonna argue to you is that these things potentially have huge health consequences, all right? So if you think about it another way, if 70% of my polymer goes into the environment and it makes micro and nanoplastics, and if it starts to kill you, then the actuarial cost, the health cost is going to get so high that it's almost better to recycle. Okay? That makes sense to everybody. So I'm coming at this whole problem from a backward point of view. I'm going to say you can't afford to not recycle because otherwise it's going to kill you. All right? I'm going to try and make that point. Make the point by showing you how micro and nanoplastics are made. And I'll also make the point that the kind of stuff you make actually has real potential to be a health problem. Okay, but that's the argument I'm going to try and make. Should I check online to see if anybody's on?
They're on all the thing you hear of people saying.
Okay, well, just check.
It's not listen.
I don't know what it
It's
is.
like
I'm-
someone else thinks that.
Okay.
Maybe you can mute that. but
I don't care, you know.
If you hear a thing, someone else. Think.
I literally don't care. It's like whoever joins, as long as they ask, you know, don't go to sleep on me from back there, I'm okay.
Well, it could be the Doge guys. Too.
So
I
these,
love Doge. He's so thin.
I don't know how he does it. Hey, so definitions, right? Microplastic, 3 millimeters to 1 micron. Any idea where that 3 millimeter number came from? Nobody has a clue. How many of you use exfoliant creams to wash your face? If you look at it, it's got a texture in there, right? Feel it the next time. They put in 3 millimeter plastic particles in there to give you that abrasion effect, right? And then they realized throwing 3 millimeter particles out into the ocean is not a good idea, so they converted to cellulosic. So that's where the 3 millimeter cutoff comes from. So anywhere from 3 millimeters to a micron is microplastic. Below a micron to about a nanometer is what I'm going to call nanoplastic. These are words that are used out there just to make sure we're all talking the same language. All right. This is all from the literature. Picture on the left is from Science magazine in the last month or so. And this is our current state of understanding. It's everywhere in your body. It's crossed the blood-brain barrier. It's in your brain. They said it's about 1 milligram of plastic. But basically, it's like taking 1 spoon of plastic and sticking it in your brain. Okay. I don't know if that's good or bad for you, right? But it's there. It's there everywhere. So remember that you're breathing it in. It's going through your skin. Okay. This, if you go and fish any water, the top picture is from BBC. It was somebody went to the Great Pacific Plastic Patch and just fished stuff out, and they found that. This is all the stuff you can see. That means the stuff smaller everywhere. Okay. A friend of mine went down just off the east coast of South Africa. There's a deep down there. He went down 5,000 meters. At the bottom, he found polystyrene, polyethylene terephthalate particles. So it's all over the place. All right. This is my hometown in India. Right? That doesn't sound quite like a river. It seems more like a plastic garbage patch. All right. So there's plastic in your body. Who cares? Do you care? Nobody cares, right?
The evidence is starting to grow. This is what scares me. This is New England Journal of Medicine, all right? Very small study, 300 patients, all right? They picked the study out, and roughly 150 of them, they went and looked at arterial plaque, and they found micro nanoplastic. The other half did not have any micro nanoplastic. The people who had arterial plaque had higher incidence of stroke, heart attack, et cetera, et cetera. And this is kind of canonical of what you look here. CD68 is a heart attack monitor. People without micro nanoplastic, you see that? They're pretty tightly bound. With micro nanoplastic, it's all over the place. So CD68 sometimes gets overexpressed when you have micro nanoplastics in your plaque, all right? Does this prove it's a problem? No, but it needs more investigation. This is a study with 300 people. You need 300,000 people to be investigated before you know it's a real problem. So that's sort of where we are.
People not have micro nanoplastics if everybody has micro nanoplastics.
There must be a threshold.
Okay.
I don't know. I'm just telling you what the study is,
Yeah,
right?
right.
I have
I'm
no
just
idea.
wondering how you.
I guess it, but I don't know, but because they found micro nanoplastics even in the Antarctic, so I have no idea, right? What do I want to tell you? Oh, there's a set of articles I'm reading now, right? People have been studying nanoparticles and their effects on health, right? Silica, most famous thing you can think about, right? People looked at amorphous versus silica nanoparticles, and they found amorphous stuff did nothing. I mean, if you had a lot of, they took rats and they overfed them amorphous silica particles, right? Through their breathing. And so what happens? They get swelling, they get lots of inflammation. But if they take away the amorphous nanoparticles, let the body heal, it would heal. But if you put silica that is crystal, which is quartz, it causes scarring, it's irreversible damage. So crystals seem to be worse than amorphous, but that's in the context of nanoparticles, right? So there's a lot going on here. Nothing is really fully understood, but it's starting to be anecdotally stuff that's happening, okay? And so I don't want you guys to panic. There's lots of plastic in your body. There might be evidence that it's starting to have a huge effect, but that's where we are. The field is really nascent. And I'm going to sort of offer you an argument where I think as we go forward, this problem is only going to get worse. Okay, that's sort of where I want to be. I'm sort of thinking first, I think, in this field. So everything is going to be sort of wishy-washy. Right? All right, this is 2019. How many of you drink out of a plastic bottle? I see 1, 2, 3. Okay, read that, please. It's 1 million particles per liter. Okay. So we said, let's sort of do an experiment. Let's try and understand what the hell it's really doing. Why are you laughing at me?
No, because I was thinking about the water bottle and you mentioned those guys.
Yeah.
How to drink their water
That's
bottle.
not my problem. He's smart. He's got a medal. Well, we'll find out, right? So this is the experiment I did, right? We took 3 millimeter size PET particles, okay? Put it in a beaker, just water, and then stir it. Okay? Simple experiment. What do you expect to see? Anything at all? Nothing? Good. Anybody else say nothing? I mean, I'm not stupid. I'm not going to show you nothing, man. I know my talk feels that way. But that's where we started out with, right? It's 3 millimeter size particles in water. PET is denser than water. It sinks to the bottom. No problem. And I stir the stupid thing. That's all I'm doing is stirring, right? 3 days of stirring. What do you see now? Some particles that you can see. 21 days of stirring. What do you think now? You want to be drinking that crap? Put it under microscope, electron microscope. That's what you're drinking. 500 nanometer size particles, platelet-like, okay? Why is this a problem? Any idea? Why is the size a problem? Yeah, don't raise your hand, just talk.
If you're ingesting it.
Maybe, any other ideas? Somebody had something to say. Heard somebody start to talk and then shut up. How many of you know the word endocytosis?
Related to cell.
Yeah, it can get, At this size, the cell is several microns across at 500 nanometers, it's just the right size, but the cell can take it up. So it can go into cell. When it goes into cells, goes into the nucleus, and start messing with the way you make DNA. Okay? Bless you. So that's why I worry about this size. And I'm going to show you more pictures, okay? But that picture should scare the living daylights out of you. Now, we did a size distribution as a function of time. This is the same PET, different days. This is the size distribution. You always end up at like 100 nanometer size with a very long tail, all right? That size does not change as a function of how long I stir. So it's telling you I'm making particles of a certain size. They break down till they get to that size, but they don't go below that size. So you're making 100 nanometer particles over and over when you stir this guy up. Okay, and that's going in your body. And that can get endocytosed by cells. That's the first thing you should be thinking about. You should be deeply worried. All right? PVC pipe.
You see the platelets, but what's the aspect ratio? What's the thickness of those?
Okay.
Okay.
Let's see what. PVC pipe, how many of you guys know what's used for?
Plumbing.
Yeah, it brings water into your house, right? And what did it replace?
Lead pipes.
Lead pipes. You all know lead's bad for you, right? PVC pipe took that pipe, put water in it, sealed it, and did this very simple experiment. Okay? This is what it makes. 400 nanometers such particles. That's the new water down there. Right? So again, drinking water that's coming through your pipes is also bringing you micro nanoplastics. So it's everywhere. No surprise, it's all over your body, right? Tire wear, you know all about that, so I'm not going to talk about it. It makes particles that goes into the air which you're breathing. Okay. Nobody following along. Suitably pissed off, suitably upset. All right.
Well, is lead worse for you or microplastic?
I don't know. That's what we need to learn.
Well, we know that is bad.
We know that's bad for you. The jury is out in micro nanoplastic, but I bet you it's not doing us any good. You'll see that as we go forward. The shapes really are problematic.
Are you for or against the plastic industry? That's what I-
Look, I created this problem, now I'm gonna fix it. I mean, that's the way to make a living, right?
For you now, but for them, they want to work for the plastic.
No, no, you guys can claim we're gonna unscrew the community, right? You guys screwed it up, the previous generation, we're gonna.
All right. Is it money?
Well, I think it's more than money, right? I mean, it's ubiquitous, right? This thing has so many plastic parts in there. You're gonna live with this stupid thing. You're not gonna get rid of my phone, right? So I'm gonna live with plastic. The question is, how am I gonna make sure that I minimize the amount of exposure? That's the way I'm gonna approach the problem. I don't think I can get rid of it actually, but I wanna make it more resilient. I wanna make it so it doesn't break up and do crap to me. So this is sort of hierarchy I expect, right? You expect that you start fragmenting a particle the moment, I mean, a polymer when you throw it out into the environment. And the logic would be as it keep on breaking down smaller and smaller, eventually I'd go all the way back down to monomer. That's what I would expect, right? But instead, what we are finding is it's making this very characteristic size in the nanometer size range, right? At least in that one experiment where I was beating the crap out of it, right? So the question I'm going to ask myself is, why do I get this one characteristic size? Are plastics sort of doomed to going to a certain size? Or is it just a transient thing that I caught along the way, all the way breaking down? That's the question I'm going to ask. And so the question I'm going to ask at the end of the day is, am I fated to get these plastic particles which are 100 nanometers in size all the time? Or is it just something that I'm catching as it's breaking down? Is that cool? Everybody understand the question? All right. And this thing happens, I showed you one example where I stir it. You can take a plastic bag, throw it out there, it's exposed to UV, oxygen, water, all sorts of stuff. Everything causes degradation of bonds. And so it's always going to be bond breaking events. So said another way, all these environmental cues break angstrom level bonds, but somehow I'm making 100 nanometer sized objects. Why? So I'm going to give you a hypothesis. This is for a non-polymer audience, so please bear with me. I'm going to remind you, polymers have tacticity. If they are stereo regular, they crystallize. If they're stereo irregular, they don't crystallize. Okay? And what fraction of polymers in the community are crystalline that we use? I suddenly started speaking Swahili.
Well, how many are clear and how many are cloudy?
I don't know, what fraction of plastics in the use are semicrystalline or stereoregular? There's a lot of nodding of heads, nobody knows, really?
How much is polyethylene?
So here's the answer, right? Polyethylene high density is about 12%. But if you do all the semicrystalline polymers, it's about 2/3 of the marketplace. 70%, all polymers that are sold are semicrystalline, okay? Remember that number.
But
But-
PET can crystallize, I mean, naturally it would crystallize, right?
Yep.
But I mean, in the bottle, it's clear, but it can turn cloudy if you put acetone on it or
Correct,
something. right?
correct.
So basically, is that crystalline or not?
PET, as you use it, is amorphous.
As it degrades, does it?
As it degrades, it can crystallize, right? The fragments that come off apparently do crystallize, but that's clearly amorphous. The bottle itself.
Polycarbonate too can crystallize.
Polycarbonate can crystallize,
Yeah.
but you know, if you look at polypropylene, polyethylene,
Right. those
that's
are
about 2/3.
semi-crystalline, yeah.
Those are semicrystalline.
Yeah.
Right? So most of the polymers you use are semicrystalline, right? And that's sort of going to become very important to what I'm going to bring. So my hypothesis is this. This is an amorphous glassy polymer, okay? I start going in there, I throw it out into the environment, starts breaking bonds at random, okay? So what's the largest, what kind of objects will I create if I start breaking bonds? This is supposed to be a class, right? So I'm allowed to ask questions. This is not a seminar, so how long do I have to go?
You've got until 11:05.
Oh, yeah, half an hour.
Then we have the room across the
I
way.
don't know, by that time, these guys will be running. Nobody's gonna come and talk for that long.
Yeah, after class, we got the room across the way for like almost an hour, so if anybody wants to, hang out.
Is it that bigger 100 nanometer particles you were talking about?
So where's 100 nanometer scale in amorphous polymer? So think about this, right? I have an amorphous polymer. It's an entangled mesh, right? Everybody heard about entanglement, right? So I can start breaking bonds. I'm going to make small fragments like oligomers or monomers, right? The largest size I'm going to get, if you think about a cross-link rubber network, is the distance between cross-links, right? Or in an
Surface
entanglement.
energy, it's the surface energy to the something else.
Correct.
right? Ratio. is
Yeah.
beside this.
You can decide that, but if you just start breaking bonds at random, the largest size object you're going to create is going to be under quiescent conditions. I don't have external driving fields or whatever. It's going to be the distance between entanglements. Okay? That number is what 3 nanometers. And so if you use random walk statistics, it tells you for polystyrene, all the fragments you're going to make are 10K or smaller, but the objects you're going to make are small, 3 nanometers. So there's no 100 nanometer scale in this problem. Everybody happy with that? Yes, no, maybe?
Well, all right, why are you selectively slicing between entanglements? You can slice anywhere.
I can't, but it'll make only something smaller.
Right, something
Right.
smaller.
So it's 3 nanometers or smaller.
Okay.
That's all I'm saying. You only make small fragments and you take an amorphous polymer. Nobody happy so far? Well, I lost you. Yeah, yeah.
Have to break at every entanglement?
No, I'm just saying as a stochastic thing. Right, I mean, the biggest size I'm gonna make is gonna be comparable to the entanglement mesh size. You can make few entanglement mesh sizes, but it's gonna be of that order. You can't make 100 entanglement mesh.
Okay, so at small scales, the polymer's liquid, right?
Yeah.
In other words, if you look at small scales or high frequency, and
Yeah.
if you're looking at, so you're talking about mobility here.
No, I'm just talking about, I'm just randomly breaking bonds. And I'm saying, when can a fragment come up?
Global polymer chain can break easier because it's
Yeah.
have tension or something, right?
I mean, this is untensed, amorphous, sitting by itself quietly at peace. And I'm just randomly breaking bonds. He doesn't like my argument. I
I
don't
don't
know.
like it.
Did I finish saying that?
It has
or-
nothing, entanglement doesn't even exist, it's a dynamic.
So think about a cross-link rubber.
A cross-link rubber is different, yeah.
Oh, let's think about a cross-link rubber.
Okay.
The distance of the largest fragment you're gonna get is between 2 cross-links.
True,
Right.
yeah.
So I'm just dumbly extending that argument.
Well, an entanglement is a timely thing, it isn't.
It is, but that's why I said glassy bond.
Okay,
So it's frozen in space.
all right,
Okay.
I'll give you the.
I mean, look at the credibility I have, right? I'll give you the benefit.
It's like, we're talking about size scales and motion.
I mean, do you generally agree the number is small?
Yeah, you could get something small.
Okay. Contrast that with the semicrystalline polymer state. You've taught them semicrystalline polymers, right?
Yes.
Okay. So you have alternate crystal amorphous, right? So imagine I put oxygen in there. The oxygen is only going to go into the amorphous phase. It's not going to go into the crystal phase. So the bonds are only going to break in the amorphous phase, okay? Now, a key thing in the semicrystalline polymer community is I have crystals, and there are some segments that go from one crystal to the other. Those are called tie chains, right? And these tie chains are really important because without the ties, the lamellae are just kind of hanging out, doing their own thing. By tying them together, you get crystal amorphous crystal that are tied together, right? Hence tie chains. So imagine if I go in there, randomly start breaking bonds, I'm going to start breaking everything, including the tie chains. If I break all the tie chains between lamellae, the lamellae become totally happy. They start flopping, and they're going to get released. Now, the characteristic size of that lamella, the thickness is going to be 10, 20, 30, 40, 50 nanometers, but that way it's going to be microns. You're following along. Now, the crystal.
That surface tension, right, it turns into wax, right? And you have polyethylene, wax is like lamellae that aren't put together.
Correct.
Or some kind of graphite. Lubricant, right? So it isn't exactly, you can get graphene from graphite
Right.
if you use Scotch tape or something, but basically it isn't exactly like a chunk of graphite is gonna spread these lamellae all over the place.
It's going to start out as a certain collection of lamellae that are going to come off.
You're gonna have wax when you break those.
You're going to get wax.
It'll be like candle wax.
It could
And
be.
then if that rubs against something, I
Mm.
guess you get lamellae.
You get lamellae coming off.
Maybe you get when you mark with wax, you get the lamellae. something.
Exactly how they make graphene sheets, right?
Yeah.
That anything you do on it will peel off a layer at a time. Right.
Scotch tape.
So then everybody understanding the logic, what he's saying? But that's actually bad news because if I rub my hand against it, I'm going to get a single layer of polyethylene crystal coming off. And that crystal is going to go in my body. Remember, I told you crystalline silicon is worse than amorphous silicon. That's where I'm leading with all this, right? So I'm saying the fact that you have semicrystalline polymers naturally, and that's 80% of the marketplace, is guaranteeing that you're going to make these lamellar crystal structures, which are going to persist forever in the environment. And that's what's making micro and nanoplastic. That's why I should be scared out of memory. Everybody fine with my hypothesis, or have I lost you all? Cool. So this is a long introduction. Let's actually do some experiment. This is sort of the story I have. Okay? Everybody got that? So we've done now, I think, something of the order of 8 or 10 polymers. All right. We do these pairs. For example, isotactic polypropylene, atactic polypropylene. Same chemistry, right? One guy has an amorphous structure, no structure at all. This is a semicrystalline structure with lamellae. And the argument I'm making is that the isotactic should make nanoplastic, the amorphous one should not. All right, and that's generally the point. Polyethylene terephthalate that I'm going to make is about 20% crystalline. There are a few others. There's polystyrene, 2 versions, and nylon is semicrystalline. All right. The experiment's really simple. That's why I do it. This is PET. We buy sheets of PET. It's semicrystalline. It's about 30%. Cut it up into sheets, put it in water. Okay. And my student first did in water, 30 degrees, quiescent. He's not shaking or doing anything, right? And he watched it for several months and nothing happened. And he came back and said, I don't have a PhD thesis, right? Because nothing happened. Then he said, I'm going to raise the temperature. And when he raised the temperature, suddenly things started to happen, right? So here is now an experiment at 110 degrees centigrade. That's why the thing is sealed on top, because water boils at 100 degrees. You can take it up to 110. It's still water. It's quiescent, but it's now starting to break bonds. So the idea is it goes into the amorphous phase and starts breaking bonds there. All right. After 14 days, we remove the plastic sheets out. This is what you're left with. So it's starting to fragment. You shake it up, it goes back into solution. All right. But those are the micro and nanoplastic that I want to look at.
So the melting point of the
PT is 250 or something.
glass transition,
Like 70.
so you're above the glass transition.
I'm above the glass transition.
So it wouldn't just kind of make a clump, like when it's just,
What you see is what you got.
okay.
We do microscopy on this. And this slide is sort of going to be the big slide of my results.
So that would be similar to polyethylene in temperature, right? In other words, because you're well above the glass transition, but you're just something crystalline. Right.
So this is all electron microscopy images, right? look at that box on the right top. This is atactic polypropylene, right? This should create only small fragments, right? So we take a droplet solution, you cast it on a TEM grid and you look at it. Water evaporates away, and the only stuff that stays behind is stuff that doesn't evaporate, right? You see those droplets all around? Those are 50 micron droplets, all right? And what we think it is, it's making small liquid oligomers that are between those entanglement point and a distance. And those liquid-like oligomeric fragments agglomerate to give you liquid-like creatures. So that is one kind of problem, but it makes those kind of small fragments, all right? Everybody happy so far? But look at the analog there. That's PET on the upper right. Look at this picture here. This thing is what worries me. So I can see a single lamella come off. I can see clusters of lamellae. All right. What does that look like to all of you? Any thoughts? You guys are all too young to remember something like this. This was really bad for you. Asbestos. That's why I'm worried, because these are crystal fragments. Asbestos is crystalline silica. That's what PET makes for you, these lamellae.
Wait, oh, lamella is 0.01.
Correct.
So that's a stack of lamella.
That's a stack of lamellae, but you can also see an individual lamella turned on its side. Right? This is 3 nanometers.
Yeah.
Right? You can see individual lamellae, collections of lamellae, something where it's edge on. You can see the lamella the other way.
Yeah.
Yeah, you asked me about aspect ratio, that's your aspect ratio. This is the stuff I'm worried about. Every semi-crystalline polymer, syndiotactic polystyrene does that. This you can't see, it's a very large view. Isotactic polypropylene makes the same kind of things. Okay, so it's real. The crystal stuff is what's harmful. The amorphous one doesn't do anything bad. It just makes small molecule fragments. You have a question? No? Cool. So now we start seeing this, you want to start thinking like a polymer physicist and say, why the hell did it form? Okay, that's what I'm going to do. But before I do that, I want to show you data, just illustrate that the semi-crystalline ones are much more harmful than the amorphous. So what we do is we take our sample, we put, in this case, polypropylene, take polypropylene, we put it in a flask and polypropylene doesn't degrade. So we use this potassium persulfate to speed up the degradation process. All right. And then what you do is you put polypropylene film in there, potassium persulfate breaks bonds in the amorphous phase, and then you watch. Okay. And then what we do is we remove the film and do light scattering. Okay. Light scattering tells you if you have objects that are big. If there's lots of objects that are big, you get lots of scattering. If you have no objects in solution, you get no scattering. Okay. So that's the way you want to think about it. Look at that. Look at this one here. This is the semi-crystalline isotactic polypropylene. This is the atactic sample. The atactic sample scatters about 100 times less. So it tells you the atactic material, which doesn't have the lamellar structure, doesn't make a lot of micro nanoplastic, whereas the isotactic one does, and it's about 100 times more. Either
So this is static.
this is static light scattering, single angle,
Okay.
total integrated
It's
intensity.
dynamic.
We did dynamic light scattering to start with,
Yeah.
but I was hoping to get a size out of it, but then once you look at the objects, they're so polydispersed,
Uh-huh.
they're not spheres. So
Yeah.
I can't use the general ideas of dynamic light scattering.
Okay.
Right? I could get an average size, but it's kind of stupid.
All right.
Yep. Technical detail. Everybody understood that? So the semi-crystalline one does, and
Dynamic light scatters, they know about dynamic light scatters.
so the problem with dynamic light scattering is if you look at objects like this, I don't know how to interpret the dynamic light scattering and get off that because it's got sizes which are so anisotropic, right? It's not a sphere. And so I can't use concepts of, I'll get an effective size, but it has no meaning because these objects are highly anisotropic and they're also highly polydispersed. That's why I'm not pulling out a size from dynamic light scattering. But I'm going to use this count rate that I'm get as sort of a metric for what's going on. All right. So here's sort of what we get. So this is just raw count rate doing straight up light scattering at fixed angle.
So this is almost like a cloud point measurement.
Exactly what it is. Exactly. So you guys know about cloud points, right?
Something.
How many of you know about cloud points? Gently raising.
This guy could bite. He's seriously a shark. Yeah.
Afraid to ask a question.
Yeah, he's from New York City. They have a knife.
In New York, we don't have knives, we just have our sense of humor.
You carry your
It's almost as
fork,
bad.
right?
So a cloud point measurement is exactly that. You take a solution, right? If it's clear, you don't see any scattering. If it starts to phase separate, it turns cloudy, which means it's scattering light. So a cloud point measurement basically says, when I go from clear to start to getting clouded, I'm going from phase miscible to phase immiscible, right? So I'm counting amount of light scattered to figure out if this stuff's got stuff in there that's big enough to scatter. Yeah? Is that what you were gonna say?
Yeah.
Okay, thanks. So I'm basically looking and saying, I'm going to use the amount of scattered light to figure out objects, how many objects I have. So let's look at PET, right? As a function of how long I degraded it at 110C. You see the light scattering absolutely flat up to 2.5 days, and suddenly it takes off at 2.5 days. Okay, everybody see this data? What do you make of this data when you see that? I lost you guys. First polymer physicsy thing, like, get me out of here. What happened when you see this data? My student didn't see it either. I had to sit with him for like one whole day, and suddenly it hit me, right? Not him. Walk me through that. Look at that data. What does it teach you?
That's how long it takes for like the majority of the bonds to start breaking down. It's got most of its structure intact for
Correct.
2.5 days.
For 2.5 days, nothing happens. You're just breaking bonds, right? But nothing has been released into solution. And then suddenly at 2.5 days, stuff starts going into solution. That's just the right size to scatter light. Okay, so it tells me no micro nanoplastics get made here. They start getting made there, and it's going up linearly with time. So that means it's constant rate of production. So this is what they call an induction time. That means things have to happen for 2.5 days before I start releasing micro nanoplastics.
But you're measuring a fixed angle, right?
Yep.
So you could be making larger things before that.
We tried different angles.
Okay.
Nothing happened. You guys have a question? Ask.
I know you explained the 110 Celsius.
Yep.
before, But how does that correlate to like the degradation on Earth?
I'll get to that. Very important question. I'll definitely get to that. Just hold that thought, right? As he talked to you about time temperature superposition. So what does that tell you? It's happening at 110 in 2.5 days. What's going to be at room temperature? Couple of months. That's his guess. Any other guesses? Everybody understand the question? So it happened in 2.5 days at 110C. How long will it take at room temperature? I have a couple of months as one guess and lots of nodding heads, right? Years, another guess. I'm just going to hold all you guys to this, right? Any other guesses? Couple of weeks. Okay, cool. Any other ideas? A couple of days, couple of weeks, couple of years. Yeah, everybody happy with those? He's snickering at the back saying, you idiots all guessing wrong. So this is polyethylene terephthalate. There's an induction for the crystalline sample. You go look at this one. This is a bunch of polymers. So one of them is, let's just look at isotactic polypropylene. That's the red dots. You have to wait 24 hours in this protocol. The atactic does nothing. Again, telling you that you're not making micro nanoplastic with the atactic, you're only making it with the isotactic, right? So again, crystallinity is being brought to the bear the whole time. Nylon does exactly that, okay? This is what the surface looks like. So on the left-hand side is the film surface. It's just optical microscopy. It's nothing, boring. That's why the picture on the left is really small, right? And this is PET surface. This is polypropylene. It's all cracking at the surface. This looks like a dry lake bed, right? You guys have all seen pictures of that. So it's breaking stuff and it's sort of creating cracks and stuff like that. So it's making a mess of the structure, but this is how the micro nanoplastics come out. It's a surface film. Now, you asked me about temperature dependence, right? So this is polyethylene terephthalate. Again, count rate is a function of time degraded. This is at 110C. It's 2.5 days. You go to 100C, it's gone up to 12 days. So it's slowed down by a factor of 5, going from 110 to 100. Now, with that information, how long do you think it'll take at room temperature? Anybody want to modify their guesses? Hours, weeks, days, years, ideas? years. Any other thoughts? Somebody is breaking into class. Amazing. What's breaking out is what I
I heard that was free beer.
get. I'm going to get back to this, but it turns out that at room temperature, this process is what works. It's going to take 50 to 100 years to make micro nanoplastic. Now, why am I worried about that? How long have you been making PET for commercially? 50 to 100 years. So it's no surprise that this stuff's starting to happen. And I'm worried that we are just in the right time range. We're going to be making crap loads of this stuff because that's a natural time scaling problem. And so that's why I'm really afraid we're going to get a nanoplastic tsunami happening. Okay, we'll get to that. You going to say something?
So is this worse than like, some very like, India where?
Nothing is worse than India.
Or, well, worse than India rather than like Canada where you have the average temperature difference, between the two of like, India probably is more like, it spends more time in the 30 to 35 degrees.
Oh. Things are happening. And anytime it's hotter, I mean, you can see here, 10 degrees changed the whole thing by about an order of magnitude, well, like a factor of 5. So in 20 degrees, it's going to be an order of magnitude.
Yeah, look to India, you see the future.
Yeah, that's another nice way of saying it. Yeah, look to the Indians. So one thing we did do is I'm now going to focus not at 100 or 110, but at 105, because that's sort of in the middle, right? And 105, if you believe this, the degradation time is going to be like 7, 8, right? So we said, let's go do a detailed study. So at 105C, we took our PET sample, we degraded in water, just took the polymer that was left behind and measured its molecular weight, okay? And that's the molecular weight as a function of time, right? And at 7 days, which is where you start making micro nanoplastic, the molecular weight we got was about 12 kilodaltons. Okay? Why did I do that? Why is that important? I also put up there the entanglement molecular weights for PET is about 4 kilodaltons, 3.5 kilodaltons.
So the size of the fragment related to the size.
I'm sorry,
The size of the fragment you can get from the molecular weight.
I can, but I mean, I told you that the fragments are related to the crystal size, right? Why am I bringing up entanglement here? If you take an amorphous polymer, right? If you go below the entanglement molecular weight, the whole thing becomes fragile, it falls apart, right? So I'm saying, even though this thing is degrading at 7 days when it makes micro nanoplastics, the molecular weight's too high for it to be unentangled. It's high enough in molecular weight, the stuff is still highly entangled. So it's not an entanglement issue, it's something else that's driving. That makes sense? Or have I lost you?
This is kind of specific to PET.
Yeah.
Because it has ES differentiation reactions, right?
What about it?
Well, that's a special, it doesn't apply to polypropylene.
Correct.
But polypropylene has hydrogen abstraction reactions, I guess,
Correct.
other reactions.
I don't care about the chemistry. I'm a physics person.
Yeah, the rate of those things are going to be different.
The rates are going to be totally different, right? But the mechanism is what I'm carrying. So it's not like I'm losing so much molecular weight that I'm dropping below the entanglement threshold and becoming brittle and creating micro nanoplastic. I'm just sort of saying the mechanism cannot be embrittlement that way. It's embrittlement because of some other factor. Okay? And the idea I'm going to go back to is this crystals being connected by amorphous phase.
Okay.
Right? So this is just a question of how this thing falls apart, right? That's why you're making micro nanoplastic. And so we said it must be mechanical in origin, must be a fracture problem, right? It's almost think about I'm breaking bonds somehow and suddenly the material is fractured. That was sort of the thinking, but that means I had to go learn a technique called fracture mechanics, which I know nothing about. So I'm going to walk you about something I know nothing about, okay? So this is all at 105C. What you do is this experiment called the double notch experiment. You take a piece of plastic, you put 2 notches in it, right? You leave a piece of
Oh,
plastic
yeah,
in.
5.
Oh, I'm not going to get anywhere close to the end, right? You leave a piece of, say what?
There's more to know then, that's good.
Well, I got about 1/3 of my way through, right? And this is always how this works. So you got, that piece of plastic in the middle, that's L, and then you pull, and you ask how much work do I have to put to get the whole thing to go to failure? Okay, so that's what I'm plotting here. That's the work to failure as a function of that ligament length, all right? Now there are two pieces to it, right? When I pull a piece of plastic apart, I have this zone here of plastic deformation. And then there is the essential work of running that crack through the sample, all right? So it turns out, if you take plots like that, and take it back down to the origin, that gives me the essential work of fracture. Okay, and there's a reason for that. That equation up there teaches you that. If I had more time, I'd walk you through it. Again, it's fracture mechanics, which I understand nothing about. There's a contribution of plastic deformation, which is the slope of the curve, and that intercept tells me the essential work of running a crack through the sample, all right? So you can take that essential work of fracture, which is the amount of energy you need to run a crack through, plot that as a function of aging time on the left. That's the red points. And what do you see? You find that that goes to 0 at 7 days. At 105C, that's when I started making micro nanoplastic. So it tells me whatever I'm doing to break bonds, at 7 days, the sample becomes so fragile that a crack runs through spontaneously with no energy. And that's the point at which I make micro nanoplastic. So it's telling you there's a deep connection between breaking bonds, getting to failure. And when you start reaching failure, you make micro nanoplastic. So it's very simple. The material is starting to lose integrity because the amorphous phase tight chains are getting cut off. And that makes my bonds for me. That makes my micro nanoplastic. Everybody happy so far? Do I want to keep on talking? So we can actually do some math.
You have like 2 papers in press, right?
Yep.
Nature and.
This is the Nature paper.
Soft matter and nature.
This is the Nature
So I
paper.
can post those.
It's available on the web.
Yes.
Yeah.
Maybe we'll go through them next week or something.
Yeah, please do. It's fun.
Yeah.
But I'm going to end here, right? So we can
Usually I
actually
trash the papers though, like every week I find them.
go right ahead and trash
I got
it.
that.
Go right ahead and trash it. I won't be here to see
There's been
it.
one paper we covered that I haven't trashed.
This actually is a pretty nice paper. I like this paper.
No, I like what you've done.
So I don't want to go back to this part of molecular weight as a function of time, right? So I told you it started with a 30K PET. And when the molecular weight reaches about 10K is when I'm going to create micro nanoplastic, okay? So I take a chain of length 30. After the degradation for 7 days, the molecular weight's 10K. So how many cuts did I put in that chain on average? So I made 3 pieces, which means I had to put 2 cuts in it, right? So this is all I'm saying. Roughly, when you do the exact math, it's 1.5 cuts per chain, all right? So I have 1.5 cuts per chain. The chain length was 105. It's 27% crystal, so the cuts are only happening in the amorphous phase. I run through the math, it tells me I'm only breaking 2% of the bonds when I'm starting to make micro nanoplastic, okay? So very, very, very few bonds is what I'm cutting before the whole thing forms micro nanoplastic. That to me is very scary because it's telling you I don't have to do a whole shitload of degradation before this thing starts to make micro nanoplastic, all right? So when you make these pieces, it's going to be crystals with lots of amorphous phase coming off. The amorphous phase is going to degrade away slowly. The crystal is going to be left behind. And that's the stuff you're imbibing. I have fear because the shape looks like asbestos. It's crystal. We know crystal is bad. Amorphous is not a problem. Both those factors are why I'm really worried about micro nanoplastics being a health concern. I have a minute to go. I want to wrap up. There's lots of math we did. Don't worry about any of that. This is the picture I want to end with. This is data for PET. I showed you before 110C, 100C. Somebody went through and measured reaction kinetics for the degradation of PET as a function of temperature. Okay, and if I take my 2 data points, put it up there, it follows exactly the stamp temperature superposition. Why am I seeing a break here? Anybody know in this curve? This is PET degradation by water. Any thoughts?
So we just what you have in the caption about the word teacher.
It's there. So this stuff is below TG and that stuff is above TG. You see a break. But if you go down to
Does
room
the
temperature,
WLF gonna go right through that?
Yeah.
And, I mean, in other words, so the TG is just like a thing at our temperatures and, or at our time scale or something like.
so you just don't worry, this is some data we got from
Yeah,
temperature.
okay.
But if you look here between 110C and 25C, there's about 3.5 orders of magnitude, right? So something that took 3 days at room temperature at 110C will take 50 to 100 years at room temperature, right? This is the reason I'm really concerned that we're going to be making lots of it because we've been using plastics for 50 to 100 years. That's your problem, all right? Not going to bother with the rest of it. But what I want to leave you with is really this, that this fragmentation is happening because you're breaking bonds in the amorphous phase. Most polymers are semicrystalline. Only 2% of the bonds have to break to make micro nanoplastic. You can continue to break away the amorphous phase. The crystal, nothing going to happen to it. Nothing is going to go in the crystal and break it up. So this stuff's going to persist for much, much longer than the amorphous phase. That's why I'm seriously worried, because this stuff's got the right size. It's 50, 100 nanometers this way, and microns the other way. And this cells start to create problems. We should be really worried. Hopefully this gives you a sense of what we're doing in this. Thank you.
Oh, we have the room across the way, the 616, if people want to talk.
Or if you don't, either
I undergrads, if you're interested in my grad school at Columbia University, in New York City, Broadway, Knoxville, you know. So, anyway. That's been the avenue.
Sorry, I showed up late. I had other random stuff to run.
Why do you have a sticker on you?
I have to go to a undergrad recruiting event in about 5 minutes. So I won't be able to. But around the cross.
Very nice.
Glad I. It's not gonna stop it.
He's an ex-PCS guy. He's
DNL. Lisa was already getting
Hey, Greg, this is Peter. Could you give me an update on what you're planning for lunch?
That's why.
Yeah, remember that expensive?
Yeah, okay. So, that part, there's a lot of smart focus.
Basically, all.
Oh, yeah, I saw it hanging a couple of weeks ago.
Yes, you're right, you asked for yourself. Okay. I think I'm gonna retire before.
I don't, he's officially not teaching anymore, but
That could be true, yeah.
he's very happy with it.
Yeah. I know he's pretty active. I was talking about kind of data reflection and.
How long have you been here?
2 years.
So starting now. It's a good time to get started.
Yeah. Well, I mean, when I did start it, okay.
Hey, how's it going? Yeah, how you doing? Yeah. Good, yeah. So you went to the doctor? Yeah, you look better. Yeah, that went okay. Or?
So, she told me that that's the processing.
I was telling you.
My ears.
Uh-huh.
So, the total bills,